Welcome back to ECE 207. Today what we want to go over really is Chapter 5, but before we do that I want to remind you that we have a couple of homework problems or sets that are due. One of those is due next Tuesday on the 5th, and the homework number 4 assignment is due on the 7th. I'm assuming that you have enough background information to work homeworks 3 and 4. Those essentially correspond to Chapter 3 and Chapter 4 material. What we want to do today is actually move on into Chapter 5. We'll do that first by trying to motivate the need for why we're working sinusoidal steady state analysis type problems, or how we can do that, or why it's significant that we can isolate on those particular problems. We'll be playing a lot with complex numbers now in sinusoidal steady state analysis, and because of that I want to provide a little bit of a review of complex numbers. Hopefully that's what it is. Hopefully it is a review for you. If it's not, then you may want to spend some time trying to get back up to speed or learning complex numbers a little bit better than what you have in the past. Then we'll move into playing with sinusoidal variables, defining those and observing or working through some of their properties. And then we'll start Chapter 5 material by looking at the average power in a resistor. We'll probably then be out of time by that point in the lecture, but we'll see. If we have more time, then we'll start introducing what's known as RMS, or root mean squared, values for periodic waveforms. We might actually get there. Let's start then the material by saying we're now into Chapter 5, and you might be asking, well, why are we spending an entire chapter maybe, or why are we concentrating so much on sinusoidal steady state analysis? Why does that get its own chapter? One way to think about this is to remember what was happening in Chapter 4. In Chapter 4 we were solving these differential equations, and when we were doing those differential equation solutions, we were actually making those have two parts. We had a natural, what we were calling a homogeneous solution and a particular solution, or you could think of those as being a natural response and a forced response. You might go back and look at example 4.4 on page 171 to refresh your memory, but in that particular, or with all of those solutions in Chapter 4, we were looking at the complete solution, let's say, of the capacitor voltage being given by two parts, one part the homogeneous solution and the other the particular solution. Those two parts then we can think of as being made up of the natural response and the forced response. The particular solution is what was being created by the forcing function. That's why it's called the forced response. And the natural response is what actually would happen in our circuit or in our system if we did not have a forcing function, but we're only looking at an initial condition response or the natural response. If we're thinking about the natural response, I tried to indicate or talk a little bit about that before, but now, in terms of the natural response, how long did that last in time? Or now I'm asking the question, how long did the natural response last? When you're thinking of natural response, if you had, in our examples, we really only had one energy storage device, and consequently we only had one time constant for that particular circuit. And that time constant was either this RC time constant, or which was in a resistor capacitor circuit, or it was L over R, which is in an inductor resistive circuit. If you had more energy storage devices, you could have more time constants. What we would want to look at in that case is the slowest time constant, or in that case actually the longest tau or time constant. Once we've identified the longest time constant, we would say, well, roughly then, after 5 time constants, our natural response has now gone away, or it only has lasted 5 time constants, which time constants in an electrical system are not very long, and that means that usually these transients disappear quickly. As an example, if we had a time constant tau that was 1/4 of a second, or 250 milliseconds. If our time constant is 250 milliseconds in length,